Okay, so now we're recording. So essentially we had a question like this with some randomness to it. And let's just identify the denominator is 4s. Oops. The numerator is 4s. And the denominator as s cubed minus s squared minus 2s plus 7. All right. And that these sign changes here are going to cause some roots on the positive side of the complex plane. So that's what we have to fix. All right. So let's put it into our equation, right, which is this. Right, so this would be the third integrator. That's where the output would be coming from if you were doing a DF2 type implementation. All right, so here's our numerator, here's our denominator, right? 1 plus g of s and notice I multiply this through. So really we get the original numerator in the numerator, right? We get the original denominator, then we get the original numerator times our g of s function. So rather than write that out and take all those steps, I just know that I can put the 4s here, s cubed minus 9s squared minus 2s plus 7. That's the original. Then I'm going to have some kind of g of s times 4 of s. And so I need to make that somehow positive and make that positive, right? And I have something times s. So whatever my g of s is, one will have to be s of some sort times a constant, because that'll give me a constant times 4 times s that I can turn that positive. And here I already have an s, so I can multiply by a constant, all right, because I've already got it. So we could say g of s1, right? There's my original numerator. What when I multiply g of s times something will give me this, right? Well, I need squared. So, right, oops. So this times this will give me something to increase that. So G1 of S will be some constant I'll call it K1 times S, right? And then G2 of S, I'll just give it another constant name. I don't need to multiply it by S, all right? So now I have K1 S minus 9S squared, right? I have to make that equal, greater than 0. And then I have K2, oops. Sorry, I left off the 4 there. 4K2S, that's S squared, minus 2S. And that has to be greater than 0. So anyway, you can just finish off the math from there, but that's how you determine your various G of S's. You can do it more formally, but basically I have G of S times a numerator, and I have to either keep multiplying by an S to get a term that's either missing or negative. Or if I had S cubed, I'd have to be dividing by S. I'm not going to go over a control problem with the fourth order. All right. Because there is something not quite right about the way Descartes' method was presented to me. It works for third, second, first order, but something, I was coming up with an example for fourth order, and something is not quite right the way they're presenting it. And so I have a feeling I have to double check, but I can't really say that this method works above where we just check the number of, make everything the same sign. Doesn't necessarily work above third order. And I have to get to the bottom of that. Maybe there's something that I misinterpreted, but when I went to go prove it with some examples, it stopped working. Okay. Now this one, this was always here. This term was always here. It just would be negative, and this could be negative or it could be missing. But if this term were missing, then the denominator would change. And it was that kind of special case I showed you during the review. So I just avoided that. So regardless of the setup, each one of these, either the parallel or the series, they were either parallel or they were in series. Okay. And so, which are kind of like, straight in the book. So, but the first one would be this, and this one would be now. This is the series conviction. The series connection, and you really get S squared plus. And this is the parallel one. It's got a different numerator and denominator. All right. Now, really, what happening is in before, if these are all real numbers and exist, they're all in control, right? If the signs are all positive, nothing's missing, these are all systems are in control. Maybe they could have complex roots, but they're in control. They're not integrating, or they're not oscillating, and they're not having exponential increase. So in this one, I say the rod turns into a solid piece of metal, right? And now we just have this, which now there's nothing resistive to dissipate the energy, and it turns into an oscillator. This one, we say it breaks away and just leaves. So you just get rid of it, and you're left with the same thing. So they both turn into oscillators. All right. Now, if I said this just flew away, well, then it flies up. The car it's disconnected and it would just fly. So I wouldn't ask that, right? And here, if I made this into a solid rod, well, then nothing would move, right? So V out would equal V in. And so, those I thought were a bit of a trick question. So it was really getting rid of the resistor. You didn't really have to.
So you're saying that it turns into a wire, Professor?
Not a wire, but a stiff rod, right? In one case. In this case, it turned into a stiff rod. It froze. So now it's connected, right? Completely. So it conducts everything, or it resists nothing. And so either R and R would go to 0, right? Here, when it flies away, the resistance actually goes to infinity, which drives this to 0. And that's where you get the purely complex, purely imaginary poles, and you get an oscillator. Um, damper brakes and is completely disconnected from the wheel in the car. Okay. Try to be as clear as possible. Completely freezes into a solid rod. And I believe this one breaks, so it's completely disconnected. Okay. So each one was a fourth order. One was a notch that you had to sum 3 terms, and the other one was a band that you had to invert a term. So it's fourth, they're both fourth order. So I draw 4 integrators. And yeah, if I'm drawing it in a kind of a regulated way, that's because this is a very algorithmic type design. You could easily program the drawing of this for n number of stages. Okay. So these are inverting integrators and we need negative feedback. So the odds are already integrating and inverting. And so we bring them in on the positive side so that they stay negative, right? These are all even. So minus times a minus is positive, right? But we need negative feedback. So we bring it in on the inverting side. That makes it negative. Now I have 1, 2, 3 inputs here, 1, 2, 3 inputs there. Okay. And I balance the summer, right? Now the way this works is that this, rather than necessarily calling things the high pass node, this node, right? This will be the highest order. So this will be the S fourth node. This will be the S cubed, S squared, S, and S to the 0 node. And this is of the numerator, right? So for low pass filters, you have no S term. You take it from here. From high pass filters, you have the order of the polynomial for a high pass is the same for the numerator is the same as the highest for the denominator. So it would come out here. All right. Now, for the S cubed question, right? This is actually minus. So to actually complete it, you have to invert it. And you can just set these two equal to each other. All right. Now, the other one, there was an S to the fourth, there was an S to the 0, and there was an S squared so we have to sum that, so we need a summer. So I just draw out the summer. Right? These are all even, so they don't need inverting. And let's just call that the SO node, the S squared node, and the S quadrupled node. 1, 2, 3. I need to balance it. 1, 2, 3. All right. If the numerator and denominator constants aren't the same, yeah, these resistors have to change, but you just had to architect it out this way. So some of you had to invert it, and some of you had to sum it. Okay. But really, drawing this is kind of, you'd either have it memorized or you could look it up, right? The thinking part of this question, or the addition, is where do you take the output and do you invert it? Where do you take the output and do you sum it properly? Okay. I'm going to do this one first. So we have 4 different time functions, and then we have 4 different fast Fourier transforms. All right. And so we have 2 square waves. They have the same period, the same fundamental frequency of, that's 1 millisecond, it should be a kilohertz. So this has something at a kilohertz. This doesn't, because that's 2. This has something at a kilohertz. And this has something at a kilohertz. So all of these have something at a kilohertz. So I need more information, right? Now this is going from -1 to 1. And so the average is 0. So A naught is 0. So I'm looking for something with a kilohertz and 0. So here's a kilohertz and 0. Here's a kilohertz and 0. So now I'm kind of down between these two. Now we've done square waves quite a bit, and you can notice that this is 1, 3, 5, 7, and that's giving us more of the square wave type thing. And with A naught not present, this one, 3 and C should match. Oh, just because I'd rather do this one first. Okay. Now here, we've got another square wave. The amplitude is still, here the amplitude, anyway. This one does have an average, and the average should be 1, right? And it should have a square wave roll off. Well, here's an average of 1, and here's a square wave roll off. Or you should just, by the time you're done with the project and the course, you'll just recognize these kind of right away. All right. Now here we have, it looks like a pure cosine or a sine, right? But there is an average offset, right? But I really only see one, like sine waves are pure. You only get one thing, but this sine wave is off by around a half. And the period is 0.5. So that should 0.5 milliseconds. So that should be 2 kilohertz. Or, oh, these were all in kilohertz. I kept it at hertz. I didn't want to go back and edit the question, so I put it up in that note. But anyway, here's a DC offset of 0.5, A naught. Here's something at 2 kilohertz, right? And the amplitude you can see is 0.5 because it's going at 0.5, it goes down to 0 and up to 1. Now this one, right, it's kind of the hardest one to do. So I probably would leave it for last. But I'm looking at it and at time equals 0, I'm kind of going up to the smaller peak. And 1 millisecond later, I'm going up to the smaller peak. So there's something going on at a millisecond, with a period of a millisecond. All right, so we've already determined, right? This one was at this one had a kilohertz, this one had a kilohertz, but these are the square waves, right? This one was at 2 kilohertz. So really, that right there gives us 1 here. And then you see these double things with a smaller frequency. And you could estimate that that frequency would be 4 kilohertz. And really, this was just sine of a 1 kilohertz signal plus sine of a 4 kilohertz signal. Just adding those two sine waves kind of gave us this thing. If we multiplied them together, that would change the frequency. Okay. But that's pretty much my thought process on those, like how I would go about it. And it's just like eliminating and finding the best one, right? Because even if this one you couldn't get, right? You know from the other ones, right, that it's got to be that one. Now, if everything were ideal, right, this would be the gain. It's not ideal, right? And this is like some kind of sample transfer function. So that gain will be good. Some random gain will be good out to where it starts to intersect, and then it'll kind of follow. So that you can see the frequency range where it's valid, right here. So using our kind of control system methodology, right, we have this, and beta is the voltage division of these two, and it's fed back in. And we assume there's no current into that node. All right. So this is just like the control, right? Thing where we're finding Q of S. H of S, I had given some number. And I gave 2 poles. All right. So the original numerator is going to be there, right? The original denominator is going to be there. Beta is going to be there. The original numerator is going to be there, right? But when I multiply through that denominator, right, it's going to cancel. All right. So mathematically, how do we find like that point? And really, this just has to be a lot bigger than whatever this is, right? Then the open loop gains will cancel out, right? That'll be 1 over beta, and then that'll equal this. But how do we say that? Well, these are the easiest way is just to take the magnitude of that relationship because it's complex now, and just say that. All right. Now, over, under, or critical. Well, you have to multiply everything out, right? And so I get S squared plus S P1 plus P2 plus P1. Okay, well, this term is the C part. That's the B part, and A equaled 1. All right, so over, under, and critical, right? It really matters what kind of roots you have, right? If B is missing, right, that's 0, then that's 0. All you have are plus or minus an imaginary number. So you, oh no, that's a control thing. So if B squared is greater, you have 2 real roots on the left-hand side. It's overdamped. If it's equal, you get a repeated root. And if it's less than, you get a complex pair. And that's for underdamped. So really, P1 plus P2 squared greater than 4. C is P1, P2 plus beta AV, right? Greater than, over, equal to, critical, less than, complex, underdamped. So you could just put in your, so based on your values of AV, P1 and P2 and beta, right, it could be any one of them. Although critically damped is actually very hard to generate randomly to get these things equal to each other. And then any rounding in your answer might make you think you're not critically damped. So in fact, just as a heads up, I really try to avoid critically damped things because I'm actually thinking philosophically no system can truly be critically damped because let's just take this example. I take a number, add it, square it, and it's got to be equal to all of that. Now the poles are the same, right? But beta and AV, you have to have like infinite digits of precision for that to really be true. And any error in precision, and it'll be greater than or equal to. All right. But it is something that you got to know. So that's pretty much it for solutions. Everybody had different problems. I kind of solved them in a generic way or an algorithmic way, right? But just like, any exam, you have to set, looking for how you got the answer, setting it up, things like that. It's certainly not an automatically graded thing. Elevator. Oh, this one? Fixed. So this is a fixed damper, right? So one end of that resistor is tied to ground. Now, the movement of the mass is measured with respect to ground, even though it's not really connected to ground. So in fact, those two elements are in parallel. And then there's the spring. Now, here's the thing. If it breaks away and it's just no longer there, right? I just have the LC circuit. But if it froze, well, this could move all it wanted, but this mass isn't going to move. Well, Garrett, I just have to look at how you assumed it and work it through, okay? Oh, but you say you got stuck. Okay. Yeah, that wasn't intentional, Garrett, to hide that. I apologize. I'll have to look at that question. Okay, I know y'all need to rest mentally for your 112. I'll post this video so anybody can watch it. And we'll start in on the rest of the semester on Wednesday. And really, what we're going to do is use things that we've learned, but we're just going to have different applications. And so, like when we multiply cosine t times cosine t, we ultimately get twice the frequency. Well, when we multiply cosine omega 1t by cosine omega 2t, and one is a lot bigger than the other, well, we actually, that's called modulation, and that's how you create a radio. Okay? And Prehan, I please be kinder to yourself. I don't think that's true. I think if you didn't, and I haven't even graded it yet, so you could have done just fine. Okay? No, and I don't mean to yell at you, Prehan, just saying. Well, that actually, going over exam solutions was what in fact was on the syllabus. So, okay. All right, guys, I'll just end it. Remember though, there's office hours, which come with extra credit. System ID is next time, Matt. Today was just going over the solutions. Okay. That's okay, Matt. You'll see it on video. All right, guys, take care. Excuse me. Bye.